All right, everybody, welcome back to CS 125. Today is our last lesson on sorting. So it's the last day that we're going to look at sorting algorithms. We're going to finish up by reviewing our analysis of merge sort because I think that's something that's worth seeing again. Merge sort, the algorithm itself and the implementation is pretty cool. The runtime analysis is a little subtle, so we're just going to walk through that again just so I can reimplant it in your brain. And then we're going to talk about our last sorting algorithm, which is the sorting algorithm called Quicksort. And Quicksort is particularly interesting. Quicksort is probably one of the most sort of tricky pieces of imperative code that we're going to write together this semester. And Quicksort is also interesting when it comes to runtime and performance, because Quicksort is an algorithm where the behavior depends a lot on the inputs, and the best and worst case are quite different, dramatically different. And then we'll talk about some ways to, there's some ways to try to improve Quicksort to get it to behave better or whatever. But it's a fun algorithm to talk about. It's another recursive sorting algorithm. At the end, we'll kind of bring things together, talk about a couple of other considerations about sorting algorithms, and then we'll be done for the day. On Friday, we move on to a new topic. We are going to spend the remainder of the semester kind of talking a little bit about the internet and how some of the web protocols work that you guys have been working with on the MP, and also a few last little bits of Java to wrap up, like exceptions and generics. Okay, so today's overall topics on Quicksort, but before we get there, just as a warm-up, I want to go back and look again at merge sort runtime. So last time we looked at merge sort, a sorting algorithm that harnesses the fact that it's easy to merge two already sorted arrays. So if you give me one array and another array that are already sorted, I can merge them together into a larger sorted array in O(n) time. And so merge sort takes advantage of that. And it works recursively. It starts with a big array. It breaks it into smaller and smaller pieces until it breaks it down into arrays of size 1, which are already sorted. And then it starts merging those arrays together. So at the bottom of merge sort, we take two arrays with size 1 and we merge them into a sorted array of size 2. Then I have a bunch of sorted arrays of size 2. I merge them together, pair by pair, into sorted arrays of size 4. Then I've got a bunch of sorted arrays of size 4, and I merge them together, pair by pair, to merge into sorted arrays of size 8. Then I've got a bunch of sorted arrays of size 8. I merge them together, pair by pair, into sorted arrays of size 16, etc., etc. I could sit here for 15 minutes doing that in powers of 2, and that would be interesting. But I'm going to stop there. So that's the idea. And we're harnessing the fact that, again, each one of those merges is O(n). So the question becomes, when we're analyzing the runtime of merge sort, how many of those merges do we have to do, and what's the size of the arrays that we're actually merging together? Because that merge is O(n) and the size of the output array, right? So as the output array gets bigger, the time to merge gets larger. All right, so let's think about what would happen if we're doing this with an array of size 8. So the first merge, again, is essentially 8 arrays of size 1 into 4 arrays of size 2. So each one of those 4 merges produces an output array of size 2. So n is 2, but I've got to do 4 of them. So I'm going to do 4 merges that take O2 time, which is O8, right? The next step is I now take those 4 arrays of size 2 and I merge them into 2 arrays of size 4. So I'm doing 2 merges. Each merge is producing an output array of size 4, and the result is I do 2 O4 merges, which is equivalent to 1 O8 merge. So that's kind of nice, just like the first step, right? So I do 4 arrays of size 2 into 2 arrays of size 4. That's 2 merges of size 4, or equivalent to 1 merge of size 8, O(n), where n is 8. The final step is I take 2 arrays of size 4 and I put them into 1 merged array of size 8. And again, here we think about the size of the output array. I've got to do 1 merge, but the output array is now n, where n is 8. And so I've done another step where n is 8, right? So this is O(n), where n is 8 for the first set of merges, O(n), where n is 8 for the second set of merges, and O(n), where n is 8 for the third set of merges. And so now, again, the question is simply how many levels do I need? And you can think about this in either one of 2 ways. You can think about how many levels does it take breaking it down to get from an array of size n to arrays of size 1, or as we were talking about before, you can think how many merges does it take if I start with a bunch of arrays of size 1 to get to an array of size n. So imagine I start with n arrays of size 1, I merge them all together, and now I have n over 2 arrays of size 2, I merge them over together, and I have n over 4 arrays of size 4. How many of those steps do I have to do before I get to an array that's of size n, right, where I've put the whole array back together again? then the answer turns out to be log n, where we're doing log base 2. So again, if I have an array output size 32, it's going to take me 5 levels, right? 1s to 2s, 2s to 4s, 4s to 8s, 8s to 16s, 16 to 32. 5 levels. 64, 6 levels. 128, 7 levels. 256, 8 levels. 512, 9 levels. 124, 10 levels. So it's growing as O log n, where we're doing log base 2. And, again, there's sort of a nice intuition behind this. Now, you might say, well, what happens if I had an array of size 300? Well, now you're somewhere between 256 and 512, right? But it's easier to think about what happens when we do arrays that are perfect powers of 2. All right, again, here's another picture to kind of continue to drive this intuition. I'm merging as I go down. I start with 8 arrays of size 1 to 4 arrays of size 2, 2 arrays of size 4, 1 array of size 8. But the height of that tree that I've created essentially here is log n, right? In this case, n is 8. The height of the tree has 3 steps. So one of the things that we liked about merge sort was it's so predictable. This is like the predictable, the most predictable sorting algorithm, right? You don't have to worry about merge sort. Merge sort's always going to come in right at the best case. So merge sort always produces the optimal worst case behavior for a sorting algorithm. We know we can prove, and you will later, that a sorting algorithm should never run slower than n log n. And merge sort will do that. The problem with merge sort is it never runs any faster than n log n either. It always takes n log n steps. And if you go back and look at the implementation that we looked at on Monday, you can see why. The algorithm has no dependence on its inputs. So the merge step doesn't examine the elements in the arrays, and the recursive part of it doesn't either. So, if the array is already sorted, merge sort does the same thing. If the array is sorted backwards, merge sort does the same thing. So the best case, worst case, and average case performance of merge sort are exactly the same. Now again, you might think this is great. I've come up with an algorithm that achieves best case performance. And that's the case, right? But the problem with merge sort is that you should be able to do better. If I give you an already sorted array, we already saw that insertion sort will only take O(n) steps. So the fact that merge sort is taking longer to sort an already sorted array because it always does the same thing every time turns out to be kind of a problem. The other problem with merge sort is that it takes up a lot of extra space. So we think about the merge step. For every merge, if I'm taking 2 arrays of size n, I need this scratch array to work into. I need the scratch array of size n, right? So basically, every time I do a merge, I need a spare array to work with. Now, if you're clever, you can work this out so that every time you do a merge, you merge into one spare array and then you merge back into the other spare array. But I still need O(n) extra space. This is extra space. Not obviously, if I have an array with n values, the size of that array grows as O(n). Each value takes up a certain amount of space. But for merge sort, I need an extra array of size n. And that turns out to be another problem with merge sort, right? Which is I need the spare array to merge into in each step. And so you imagine you're Google and you're trying to sort, 1 trillion records. Well, okay, the first step in the sorting algorithm is find me the equivalent of twice that much space. That may be a non-starter. So that's another place where merge sort is not always the right sorting algorithm for every problem. Okay. All right. So now, and on some level, what we've been some of these algorithms, right, fall into this category that we call divide and conquer, right? And a lot of the recursive algorithms we've looked at fall into this category, right? And I just want to point this out as we move on to discuss another divide and conquer algorithm. So what divide and conquer does is it says, okay, you give me a problem that's big and complicated. The way I solve it is by breaking it down repeatedly into smaller and smaller problems until I find a problem that I can conquer, right? So at each step, I either divide or conquer. The goal is that as long as I divide enough, I get to problems that I can conquer. And so merge sort worked that way. Merge sort said, well, I don't know how to sort an array of size n, but I know that if I keep breaking it into smaller and smaller pieces, eventually I'll get to the point where I have an array of size 1, and I know how to sort that. And then I know how to take 2 arrays that are already sorted and splice them back together, merge them back together, okay? So now let's look at our next sorting algorithm. And again, this is a fun one. It's a fun one to implement. This This is one of those ones where I always cross my fingers that I'm going to get it right. Do a little practice beforehand. But let's talk about how Quicksort works. Okay, so what Quicksort does is that in each step, Quicksort picks an item called a partition. It picks an item called the pivot value. And then what it does is it partitions the array around the pivot value. So I pick a pivot, and then I have a step that we're going to implement together today where what happens is when that step completes, all of the values that are less than the pivot end up on one side of the pivot, and all the values that are greater than or equal to the pivot end up on the other side. And so what happens is I've split the array, I've partitioned the array into values that are less than the pivot and values that are greater than or equal to the pivot. And it can be less than or equal to and greater than, it doesn't matter, right? The idea is that, the pivot is in the right spot, but on one side of it is an unsorted array, but that unsorted array is smaller than the original unsorted array. And on the left side is an unsorted array, but that unsorted array is also smaller. And critically, I know that none of the values from the right part belong in the left part and vice versa. Okay, so it's easier to look at. So let's walk through it together. So in each step, I pick this pivot value, and then I divide the array into these two parts, larger than the pivot, smaller than the pivot. So let's see how that would look. Let's imagine that I choose a pivot value of 8. Okay, so 8 happens to be the first value in this array, and then here's what it looks after the pivot. Okay, now note, I did not sort the array. What I did is I partitioned the array. The values to the left of 8 are not sorted. They're still unsorted. I've got 5 before 3, right? So the red part of the array, not sorted. The other part of the array, in many cases, is also not sorted. In this case, it turned out it only had one value in it, so it is sorted, but it's not guaranteed to be sorted. So when I'm done with each partition step, I have two smaller unsorted arrays. But here's the critical part. Here's how I'm making the problem smaller. None of the values, in this case, so none of the values in the red part of the array belong in the blue part, and vice versa. So I know that I can essentially proceed as follows. Now I'm going to sort the red part of the array, and I can ignore the blue part. And in parallel, or at the same time, in another series of steps, I'm going to sort the blue part, and I know that I can ignore the red part. So by partitioning the array, I very cleverly have split the problem into two pieces. And again, as in many of our recursive algorithms, our goal is to divide the problem until it's easier to solve. So now what I've done is I've divided the problem into two smaller subproblems. I have the values that are smaller than the pivot that I still need to sort, and the values that are larger than the pivot that I still need to sort. But each one of those arrays turns out to be smaller than the original array. The other thing to notice is that the pivot value always ends up in the right spot, okay? So the pivot value after each step is sorted. So that's one value in the array that's put in the right position. So even if nothing else good happens, I know that I've at least put the pivot in the right spot. Okay, so now let's imagine how this would proceed. So now I've pivoted the array around the value 8, or I've partitioned the array around the pivot value 8. Now I'm going to repeat this step. And in this example, in each step, I'm picking the first value in each array as the pivot value. So now I'm choosing the first value from the unsorted part of the array that's to the left of the pivot value, and I'm choosing the first value in the unsorted array that's to the right of the pivot value. Now, this unsorted array that's to the right is already sorted because it's of size 1. So I can really kind of ignore it, right? Where I really have to do more work is over here. Okay, so now I'm picking 5 as my pivot value. And again, I'm going to pivot that smaller array around the pivot value 5. I'm going to partition. I'm really getting those two things confused here. I'm going to partition the array around my pivot value 5. So now, again, let's see what happened. 5 ends up in the right spot. I have two values left over here that are larger than 5. So I have this smaller array over there I still need to sort. And then I have this smaller array to the left of 5 that I still need to sort. But critically, 5 is in the right spot, and none of the values to the right of 5 belong to the left of 5, and none of the values to the left of 5 belong to the right of 5. Okay? So I've created two smaller problems. I continue doing this. So now I have this small array of 3 values that I still need to sort. So I pick a pivot value, which is my first value 3, and I partition the array around that pivot value. And now I'm getting close, right? And it turns out I'm actually done. I just haven't realized that yet because what's left are these small arrays of size 1 that I know are already sorted, okay? And pretty soon I'm finished, all right? So again, Quicksort is, one of the sorting algorithms that I think is not only a little tricky to implement, but it's a little tricky to think about. So again, in each step, I'm not sorting the array. I'm just trying to create a smaller problem. And the way I create a smaller problem is I say, okay, well, I'm going to put there's 2 things that each step accomplishes. One is that it puts the pivot value into the right place. The second thing is it partitions the array, so it creates 2 small independent problems. After I partition the array, I know that I can sort the front part of the array separately from the back part, because all the values that are smaller than the pivot are in one spot, and all the values that are larger than or equal to the pivot are on another side. And so those now can be treated as 2 completely separate independent arrays and sorted independently from each other. So I've created, like I do in many of my recursive problems, 2 smaller subproblems. Okay, so now let's look at one step. Now we're going to actually look at what happens when we do the partition. And this is tricky. Again, this is a subtle little piece of imperative code. So we're going to walk through the diagram, and then we'll actually do the implementation. We'll come back to the diagram and kind of flip back and forth a few times to try to make sense of what's happening. Okay, so here's how we're going to do this. I'm going to pick up pivot value, and choosing a good pivot turns out to be critical to getting good performance out of Quicksort. But for now, we're going to keep it easy. We're going to pick the first value in the array as our pivot. Okay. And what we're going to do is we're going to go through the array. If we see a smaller value, we know that it needs to go, it needs to go to the left of the pivot value. And so what we do is we scoot the pivot, we essentially move the place where we're going to put the pivot value over by 1 to make space for that smaller value. And then we swap it into the smaller part of the array. Otherwise, we just keep moving to the right, okay? So here's how this starts. So my pivot value is 6. And right now, the place where I would swap the pivot in would be its current location. But this is the value I'm looking at, okay? So I look at 5. Is 5 smaller than the pivot? It is. It turns out right now, the place that I swap it to is the exactly same position in the array, so I leave it alone. Now I go to 7. Is 7 smaller than the pivot? No. So I move on. Now I go to 3. Is 3 smaller than the pivot? It is. The pivot is 6. 3 is smaller than the pivot. So I need to do something to make sure that 3 ends up to the left of the pivot value. And what I do, and again, this is tricky, is I swap it with 7. Okay? So basically, oops, sorry. Okay, so what happened is, you'll see I took 3 and 7 and I swapped them. And I moved the pivot position over one place. Okay? So you imagine if I stopped now and I put 6 right here where 7 is, I would end up with these 2 values to the right of the left of the pivot that belong there. But I'm going to keep going because I'm not done with this part of the this partition. Okay? Now we look at 4. Is 4 smaller than the pivot? It is. So I swap it with the current pivot location and I move the pivot over by 1 position. Is 11 smaller than the pivot value? It's not. So all I do is I move on to the next value. Is 8 smaller than the pivot value? It's not. So all I do is I move on to the next value. Is -1 smaller than the pivot? It is. I swap it with the current pivot location and I move the pivot over by 1. Now, all I need to do, so basically this array is finished, except 6 isn't in the right spot. I need to put the pivot value into the right place. And so what I do is I actually swap the pivot value with the current pivot location, right? So now what I do is I swap -1 and 6, and now I've accomplished what I was after, right? If I look to the right of 6, larger values, to the left of 6, smaller values, okay? I know this is tricky, right? And sort of let me go through and develop a little bit more intuition here, right? So the idea, there's 2 things going on here, right? One is that I'm making space at the left side of the array for values that are smaller than the pivot, right? Every time I find a value that's smaller than the pivot, I need to increase the size of the part of the array that's smaller than the pivot by 1. But I also need to get that value into that part of the array. And the way I do that is with this swap. Now you might ask, well, what happens if my swap moves a value that should be inside the pivot inside below the pivot above the pivot. And the idea is by choosing the location of the pivot properly, I can prevent that from happening. So you'll see here, when I swap 3 and 7, 7 is a value that's larger than the pivot, so it belongs to the right. So moving it farther to the right is okay. I did the same thing over here when I found -1. So -1 is smaller than the pivot. I'm swapping it with 7, which is larger than the pivot. So 7, which belongs to the right of the pivot, is going farther to the right of the pivot. But -1, which belongs left of the pivot, is being moved left of the pivot. So that's how my swap accomplishes this. The swap is always between a value that is larger than the pivot, that can go farther to the right, and a value that's smaller than the pivot that needs to go to the left to get below the pivot value. Okay, so now let's go ahead and implement this. We're not going to actually implement Quicksort together today, although it is fun. I'm leaving that for you guys to do as a homework problem. It'll also be on a quiz. But the tricky part here is the partition. This is really what does 95% of the work of Quicksort. When you guys actually get to do Quicksort on the homework, you'll discover that it's surprisingly easy to actually finish Quicksort once you have the partition function. The partition is what's tricky about this. Okay, so let's take a run at it. Okay, so the way that I've set this up is that I'm using a start and an end position. So rather than choosing a small array, I'm going to actually partition just a portion of the array, right? So the part of the array that I'm partitioning starts at start and goes up through end. And the way that we're going to test this is essentially by partitioning the entire array. But there is a case here where if start is, once start equals end, or actually it turns out if end is less than or equal to start plus 1, I think that's correct, then I don't have any more work to do here, right? So essentially, if my end value, if my start and end positions are too close together, if either the size of the array I'm supposed to sort is size 1, or if it's size 0, I can just return, right? Because I don't have any work to do. And this is probably, is this the right way to do this? Let's try, I mean, there's another way to write this, but this essentially is what's happening, right? So this will make sure that I don't do any work if start is equal to end, right? Because if start is equal to n, then start plus 1 is going to be start is equal to n minus 1, right? If start is equal to n minus 1, then start plus is going to be greater than or equal to n, or 1 is equal to n, and n is less than or equal to itself, right? That's how we return. Okay, so now we're going to go through the portion of the array that we're actually working with, okay? So let me write my loop first, I++. And so again, I'm not going through the entire array. I'm only going through a piece of it. I'm only going through the portion of the array starting at index start and going up through index end. And I'm not going to go all the way to index end, right? So this will be end exclusive, right? This allows me to call it like this with testArray.length and essentially partition the entire array. Now, there's two things that I need to, one of the things I need to keep track of as I go through here, and again, if I go back here, I'm thinking I need to keep track of this pivot position, okay? So that's one of the things that I need to keep track of. And the pivot position is going to start, so I'm going to say int pivot position, and that I'm going to initialize to be the start, okay? And here what we're actually going to do is we're going to go at the start position plus 1, right? So basically I'm saying the pivot is the value at the beginning of the part of the array that I'm partitioning. That's my pivot value. And then I'm going through and examining the rest of the array that I need to work on, okay? If this array only has 2 items, then I'll only look at one other item, and that's okay. It might be that I need to swap the 2 in order to correctly partition the array with only 2 items in it. Okay, so I've set my pivot position to be start, and I also need to know what the pivot value is, because that's something I'm going to be using throughout my calculation. And I could just use array start, but instead I'm just going to, I'm going to save that off into my pivot value. I'll say input array start. Okay, great. So now I'm going through the loop, and basically what I need to do is for each value, I need to see if it belongs. If the value is larger than or equal to the pivot value, then I'm done. I don't need to do anything. I just move on to the next value. But if the value is smaller, I need to do some work. So if the input array I is less than pivot value, then I need to do three things. The first thing is I need to bump the pivot position forward. So I'm going to say pivot position plus plus. This is making space in the part of the array that's smaller than the pivot value for this new value that I'm about to move in there. Okay. Then I have a swap to do. Right. I have to swap the current value I'm looking at with the value at that position, at the pivot position. Right. And so I do this the way I normally do things. I say temp value is equal to pivot input array I. Actually, we'll do input array pivot position. Then I overwrite input array pivot position is equal to input array I. And then I send the input array I is equal to temp value. Okay. And this should do it. I'm basically swapping the two values. Okay. Now this is close to being done, but remember there was one step that I still had to perform, right, at the very end, and this is actually one of the more important steps, which is that I need to put the pivot itself into the right place. So if you look at the output here, you'll see 5, 7, 3, 4, 6, 8, and -1 are all smaller than the pivot value, but they're not to the left of the pivot value. So I moved a couple of items around to accomplish this. This is not the same order that they were in the original array, but I didn't finish the job because I didn't put the pivot value into the right position. Okay, so how do I do that? Turns out to be pretty simple. Essentially what I'm going to do is I'm going to swap the pivot, the value that's in the current pivot position with the starting position. So, and here I don't have to actually use the temporary variable because I already know the pivot value. I pulled it off up here, right? So I'm going to say input array start is equal to input array pivot position, and input array pivot position is equal to pivot value. Okay, and so now let's see what happened. Okay, so did we correctly partition this array? Well, the pivot value I chose was 8. 5, 7, 3, 4, 6 belonged to the left of 8, and they ended up there, and 11 belonged to the right of 8. So let's try to put some other values in here and make sure that this still works. That seems to work. So 11 and 12 now both end up on the right side of 8. Let's put another 8 in there. Now this becomes a little bit interesting, right? Because you might argue, well, wait, it broke because this 8's all the way at the end, but my pivot value is here. Okay, so when you have more than one, when you have a duplicate in your array that's also the pivot value, you have to be careful when you look at the output to make sure you identify where the pivot position is. So the value that I was pivoting around was 8. This is the pivot position when I'm finished. You'll see to the left of the pivot are values that are smaller, and to the right are values that are greater than or equal to. That 8 that was equal to my pivot value ended up all the way at the end of the array, and that's cool. That doesn't violate our goal here. Okay, so we've implemented partition. And this is, like I said, most of the work behind Quicksort, which you guys will have the pleasure of being able to finish as a homework. Okay, good. So now let's think about Quicksort and its runtime, because this is one of the things that gets fun here, is that Quicksort is a cool algorithm. It's clever. It does a nice job of sorting in certain cases, but Quicksort is an algorithm we need to be a little bit careful and suspicious about because Quicksort can have some unexpected behavior. So let's think about best case. Okay, first of all, we'll look on the bright side. What happens in the best case in Quicksort? So now here's the trick. Here's what the performance of Quicksort depends on. So let's look back here, right? When we looked at our partition step. Actually, let's go all the way back and look at this, okay? So in merge, let's compare with merge sort. In merge sort, we divide the array in half when we're starting the algorithm. When we're going down and we're making the problem smaller, we always divide the array in half. Therefore, we always get log n levels. Now, in the best case, in Quicksort, we choose a partition value that ends up dividing the array in half. But in Quicksort, when we pick our partition, we actually don't know how many values will be to the right of the partition and how many values will be to the left of the partition. We have no idea, right? So in this case, I choose 8. After my partition, I started with an array of size 8. Now I have 2 arrays to sort. One is size 1 and the other is size 6. So it turns out that the partition didn't actually effectively divide the array in half, because I started with an array of size 8. What I would have liked is like one array of size 3 and one array of size 4. Remember, the pivot value is in the right spot, so I don't have to worry about the pivot value going forward. What I ended up with was one array of size 6 and one array of size 1. And this is the tricky part about Quicksort, right? Which is that you pick a pivot value, but you don't know how effectively that pivot value is going to divide the array. In the best case, which is the analysis that we're about to go through, in the best case, the pivot value divides the array in half. So each partition divides the array into 2 equal pieces, okay? In that case, the analysis is very similar to merge sort. So in the first step, we take an array of size n. Let's say it's for 8, right? So basically, after we partition the array, we have 2 arrays of roughly size 4. I know they're not exactly size 4. One is size 3, the other is size 4, but whatever. We're going to, just bear with me, right? Let's say that, they're both size 4. It's close enough, right? The second partition, now I take 2 arrays of size 4 and I partition them into 4 arrays of size 2, okay? Again, not exactly size 2, but close enough. Third partition, I take 4 arrays of size 2 and I partition them now into 8 arrays of size 1. And at that point, I know that everything is sorted, right? Because the partition leads to 2 unsorted arrays, but an array of size 1 is already sorted, okay? So in the best case for Quicksort, with an array of size 8, I take the original array, I partition it into 2 arrays of size 4, I partition those into 4 arrays of size 2, and then I partition those into 8 arrays of size 1, and at that point I'm finished, because each partition leads to unsorted arrays, but once I get to this unsorted array of size 1, I know that I'm finished, right? Note that unlike merge sort, there's no work that we do kind of on the way back up. So merge sort broke the array down into smaller and smaller pieces, and then it reassembled those pieces as the functions were returning. In Quicksort, we do the work on the way down. So each partition is solving a little piece of the problem, right? Because each partition is creating smaller and smaller problems where we know that the values to the left of the pivot value and the values to the right are not sorted, but they're smaller than the original array, the size of those smaller arrays. Okay, so again, best case performance for Quicksort is O n log n, because the partition, again, let's look at our partition function. This partition has to go through the entire array. So partition is O n, where n is the size of the array that we're partitioning, right? So again, best case performance for Quicksort, log n levels, an O n partition at every level leading to O n log n performance, right? That's our best case. That's all good. Now, you might wonder what's cool about Quicksort, like why is it better than merge sort? Because we're about to point out that Quicksort has some problematic behavior in certain cases. And the thing I want you to notice here is that when we did this partition, we didn't need any extra space. All we did was swap around the values within the original array. And so it turns out that Quicksort can actually be done in much, much less space than merge sort, right? And we're not going to get into the full analysis of how much space Quicksort needs, but it's basically log n space rather than O n space, right? It does need some extra space. Each one of my partitions needs a little bit of scratch space to work with to store the pivot value, but I certainly don't need a whole separate array, right? I'm just swapping values around within the original array. It's sort of like insertion sort, right? Okay. So best case for Quicksort, O n log n, and a much smaller amount of space required, extra space required than merge sort. But where does the trouble lurk? So the trouble lurks in the partition operation. Now, we looked at the best case where I choose a pivot value that divides the array into 2 equal parts. But what if my pivot value doesn't divide the array into 2 equal parts? In fact, what if my pivot value doesn't divide the array at all? What if I choose a pivot value and it turns out that all the values left in the array are either greater than or less than that pivot value? So basically the pivot that I choose either ends up where it started or moves to the other side of the array, but all of the other values are on one side of it, okay? So now let's see what happens in that case. Let's say that, so in the first partition, I take an array of size n, and what I'm left with is an array of size 7 and an array of size 1, right? You know, I have not done a very good job of making the problem smaller. I only made it a little bit small. Then I have to take that big array with all the values that were left in it and partition it again. But let's say that I have the same problem with my partition function. It doesn't make the problem into two equal parts. It instead puts all of the values on one side of the partition, okay? And this continues and continues and continues and continues. And eventually what's going to happen is that for an array of size n, I'm going to have to do n partitions. And each partition takes n steps. So I am now in an O(n) squared place, and I did not want to be in that place. This is a bad place for Quicksort. And so again, Quicksort is a fun algorithm to implement. It's also a fun algorithm to analyze because it turns out to have some very pathological behavior in certain cases, right? So in the case where the array the partition I choose ends up not doing a good job of dividing the array, I can actually have performances as bad as insertion sort and some of the simpler sorting algorithms that we saw before, right? And so in practice too, Quicksort has this liability, which is that it's super unpredictable. You can give it one array and it runs super fast. You give it another array and now it's slow all of a sudden, right? And the reason is the contents of the array are different. And in one case, your partition ended up, your pivot values ended up doing a nice job of partitioning the arrays. In the second case is your pivot values didn't do a good job of partitioning the arrays, right? Now you might wonder, what are some of the worst case inputs for Quicksort? So how do we trigger this behavior? So it turns out that if you implement Quicksort in a fairly straightforward, unsophisticated way, it's very, very, very easy to hit these pathological cases. Here's an example. This array, as you may notice, is sorted. It's sorted in descending order, but it's sorted regardless. Okay, this is a sorted array. It happens to be sorted backwards from the direction that we're trying to sort it. But let's see what happens when we try to apply Quicksort to this array. So I pick 8 as my pivot. I pick 8 as my pivot value. And now I partition the array, and look what happened. I have an array of size 7 to work on. Didn't help very much. So now I choose 7 as my pivot. Moves all the way to the end of the array. Now I have an array with 6 values. And this just continues on. So essentially each partition, I'm only increasing the size of the sorted part of the array by 1 value. And this is bad. So again, in the worst case scenario, not only does it take O(n) squared, but if I give it a sorted array that happens to be sorted in the wrong direction, and you pick the first value in the array as your pivot value, you will achieve O(n) squared performance. And so again, you can imagine applications and scenarios where I want to sort the array one way, and then a minute later I want to sort it the other way. And the problem there is that once I've sorted the array one way, if I'm using Quicksort and Quicksort is choosing the first value as the pivot when it does its partition, then it might be fast to sort the array in one direction, but once I try to reverse the array, it gets very slow. Okay? And so this turns out to be undesirable. Now, you can go online and you can read all sorts of really fascinating analysis about how to try to improve Quicksort so that you avoid this problem. And the trick comes down to the following. It comes down to choosing a good pivot value. If I choose a good pivot value, the goal is that I find a pivot value that evenly divides the array into 2 parts. Now, you might be wondering, well, why can't I choose a pivot value that just evenly divides the array? Why don't I just choose the pivot value that divides the array into 2 halves? Here's the problem. That pivot value has a name. The name of that pivot value is called the median. It's the median value, right? So a median in a statistical data set is the value where if you sort everything, it's the middle. How do I choose the median of a bunch of data values? I have to sort them and then find the middle. So I can't have a part of my sorting algorithm be dependent on being able to sort the data, because that's what I'm trying to do, right? So if I really wanted to pick the median value as my pivot, I would have to sort the array, at which point I would have solved the problem that I'm trying to solve. right? So there's no way to use the median as a pivot value. You can do a better job than just choosing the first value. So the first value will fail, will produce pathological worst case behavior if the array is sorted in reverse order. If I choose the last value in the subarray, that will produce pathological behavior if the array is already sorted. A better idea, there's a couple of different approaches to this. One is I pick a random value from the array. That's better than always choosing the first or the last because it doesn't hit these pathological cases when the array is already sorted. The other thing that some implementations do is they randomly pick 3 values from the array, and then they choose the median of those 3 values. All right, and the idea is I'm sort of sampling the array. I can't find the median in the entire array because that requires sorting the entire array, but I can pick 3 values and sort those 3 values pretty quickly and use that to choose the median of just a very, very small subset of the array. And so again, getting good performance out of Quicksort ends up coming down to figuring out how do I avoid these pathological choices of pivot value. All right, so we're almost ready to fill in our table with values from Quicksort. So in time, best case performance for Quicksort, when I choose good pivot values and I get even partitions, O(n) log n. Worst case, when I choose bad pivot values and I get essentially no partition, n squared. Average case, again, hard to say, right? Hard to say, always hard to say, depends a lot on your data, but usually you'll see this listed as O(n) log n, okay? Space, so the amount of space depends on how many partitions I have to do. It really depends because each one of those partitions takes up a certain amount of space. And so essentially, the amount of space ends up depending on the depth of the tree, which is determined by how many partitions I do and how effectively those partitions divide the array. In the best case performance, log n space, because I have log n levels going down to the point where I partition it and I'm finished. In the worst case performance, I have more levels. That's why my performance starts to get towards n squared. The space requirements go up as well, right? But, average case space utilization for Quicksort is substantially less than merge sort. Remember, O(n), you might think, what's the difference between O(n) and O log n? It's huge, right? It's a difference between O(n) squared and O(n) just in the other direction. O(n) heads off like that. You might think it's not so bad. O(n) log n, very, very gently. It goes slower and slower and slower. And so once you get to fairly big data sets, huge difference between O(n) and O log n. And so we would always pick the O log n algorithm. All right, so now let's go back and look at the 3 sorting algorithms we looked at in class. You guys will see another set of sorting algorithms next week in lab, a couple of ones before you take a quiz on sorting. But here are the ones that we've talked about together, right? So again, we moved the labs a little bit around this week. Actually, I should say I'm going to reopen. I know, so anyway, the sorting lab will be available again for you to work on next week. If you started working on it yesterday, great. You're almost done. Otherwise, you'll have next week's lab to work on that. That'll introduce 2 more sorting algorithms into the mix. But for now, the ones that we've looked at in class are insertion sort, merge sort, and quicksort. So and now let's kind of like slow down and look at both performance, but also think about when they're good, when they're not good. Best case, worst case inputs. So the best case for insertion sort is already sorted data because insertion sort in that case will actually run in O(n). Worst case for insertion sort was backwards because every time I insert a value, I have to compare it all the way across the array, and so I end up with O(n) squared performance, right? So great thing about insertion sort, best case O(n). Bad thing, worst case O(n) squared. Merge sort, best case, worst case, it don't care. Does not look at the data at all. And so it doesn't have any dependence on the data values that are in the array. Quicksort, best case data for Quicksort, again, Quicksort you end up having to talk a lot about the implementation, how does it choose pivot values, but in general, a simple implementation of Quicksort will usually do pretty well on random data. The reason for that is that no matter how it chooses a pivot value, it has a pretty good chance of partitioning the array evenly, okay? Worst case is sorted data depending on the direction that it's sorted, right? But actually, if you always choose the first value, always choose the last value, it doesn't matter, right? Sorted data always causes Quicksort to perform poorly. What about runtime? All right, so runtime, best case for insertion sort, we saw it was on. Worst case, on squared. So insertion sort is interesting, right? Because its best case is better than merge sort and quicksort. Its worst case is worse, right? So you see a much, much, much bigger divergence between how it works in the best case and how it works in the worst case, right? We know it's not optimal because the worst case performance of a sorting algorithm should never be worse than on log n. Merge sort, we get great, very predictable performance. Average case, worst case, best case, on log n. It does not care about what's in those arrays. It's going to do the same thing regardless. Quicksort, best case, on log n, and less storage usage than merge sort. Worst case, we can find pathological cases for quicksort. Now, people will usually say, a decent implementation of quicksort will not hit those on squared cases. But they're out there, right? But that's also true. A good implementation of quicksort that doesn't use bad and naive strategies for choosing pivot values can typically achieve on log n performance. All right, finally, space usage, extra memory required. Insertion sort, just that one value, right? It's like that one temporary value I needed just in case I needed to swap something, right? Merge sort, I need a whole extra array of the same size as the array that I'm trying to sort to use as scratch base when I'm doing the merges. Quicksort, again, depending on how many calls I have to make, depending on how big that tree is, it's essentially O log n. Each level of quicksort needs some extra space. So this is a case where, like many of the things you're going to encounter in your career in computer science, there are substantial trade-offs between these different approaches, right? One thing to keep in mind is that for very small arrays, insertion sort can actually be faster than merge sort or quicksort. The reason is it's simpler and it doesn't actually have the overhead of making these recursive calls, right? And there are algorithms that essentially, if you give them a very small array to sort, they'll use something very simple like insertion sort, right? If predictable performance is really important for you, so there are certain applications where, the most important thing is that the algorithm always take the same amount of time, right? It's better to be predictable than to be fast, right? In that case, merge sort is a great choice because it always takes the same amount of time and it's not dependent on its inputs. It does require a lot of extra space. If you're short on space and you're willing to gamble a little bit, quicksort, right? Quicksort uses a lot less space than merge sort, and its best case performance is just as good. And again, most good implementations of quicksort do not fall into those traps that we saw that could happen, right? Because they don't use dumb algorithms to pick the pivot value. All right, so one last thing I want to mention here is this additional feature of sort analysis known as stability. And so what does it mean for a sort to be stable or unstable? So a stable sort means that if I have two items in the array with the same value, the sorting algorithm will never exchange their positions. Okay, so if I have like 5 8s in my sorting in my array, and I sort it, those 8s won't move to a different position. Now you might say, well, how do I know? Right, they're all the same value. Well, hang on a second. Right, unstable sorts, two items with the same value may switch positions. Now, why is this important? Well, because in the real world, a lot of times we've been sorting integers, right? And that is, something that is a valid use of sorting, right? But a lot of times what we're sorting in the real world are objects, and we're sorting them based on some key. So for example, let's say I have a person class here. I know it's been a while since we looked at an object, right? I look at person class with a name and an age. Let's say that I want to sort all the people in my program by age and then by name, right? If I have a stable sorting algorithm, what happens is that if I sort by age first, I get everybody from youngest to oldest. And then if I sort by name, what'll happen is that what I'll end up with is people sorted alphabetically, but within those alphabetical cohorts, they'll still be sorted by age. Right? Same thing if I accomplish the other thing if I do it vice versa. So if I sort by name first, and then I sort by age, two people with the same name will end up sorted by age within my final sort. And so essentially when I'm going to perform multiple sorts using different keys on the same set of objects, sorting stability starts to matter. Because the idea is that the second sort that I do doesn't mess up the results of the first sort that I did in cases where the two things have identical values. So again, if I sort by name first and then by age, okay, what I want is everyone sorted by age, but within each age group, I want people sorted by name. With the stable sort, I achieve that. With an unstable sort, I don't. Of the sorting algorithms we've talked about, Quicksort is unstable. I wish actually I should know this, right? But you can look this up. Quicksort is definitely unstable. I think insertion sort is stable. Merge sort I will have to think about. I think merge sort is also unstable. All right, so the last word about sorting algorithm that came out fairly recently, right? So by recently I mean within the last 20 years. I know time is passing differently now, but it still counts as recent to me. Quicksort is an adaptive sorting algorithm. It's the default sorting algorithm that's currently built into Java and Python. So when you sort things by default in Python, if you sort a list of a certain size, you end up with having your sort done by an algorithm called Quicksort. Quicksort is far more complicated than the algorithms we talked about. That's why I don't go into it. Right? It would require at least one entire class, if not several classes, to talk about. But essentially what Quicksort is something that's referred to as an adaptive sorting algorithm, in the sense that it uses several different strategies based on the data that it finds. And what Quicksort really tries to do, or one of the observations that led to Quicksort, was that a lot of times when you're sorting data, a lot of the data within the array or the list that you're sorting is already sorted. So a very common use case is I have two sorted lists and I'm merging them into one sorted list. Okay, and maybe I have some unsorted data here and there, but most of it's already sorted. And so what Quicksort tries to do is it tries to identify runs, right? A run is a sequence of data within my array that's already sorted. So if you imagine I can identify a run, what can I do with that? Well, remember merge sort, right? Taking two already sorted chunks of my data and merging them together is ON. And so if I can identify large chunks of data within my array that are already sorted, I can bring them together in ON. Internally, it also uses insertion sort to sort smaller arrays when needed. And the idea here is, again, this is adaptive, meaning that it adjusts its behavior to the features of the data. Right? That's how it gets such great performance. All right, so I'm almost done. I'm going to leave you with, this is a fun visualization that somebody put together on the internet of different sorting algorithms. So you guys can watch this. It takes about 6 minutes to go. It has like some nice sound effects as it goes along, right? So here's insertion sort. You can see it grabbing things one at a time, moving them from the unsorted into the sorted part of the array. The sorted part of the array is growing from left to right. I've never had a chance to just sort of like talk over this before, but it's kind of fun, right? I feel like I'm trying to narrate a video game or something like that. So anyway, this is a fun visualization. Usually somebody will find this and post it on the forum, but I'll put it here for your amusement, your enjoyment. What's the next one here? Oh, here's Quicksort. Okay, yeah. So there's the first partition. Now it's partitioning the left side, partition, partition, partition. And you'll see as it finishes the partitions, bigger and bigger chunks of the array are actually ending up being sorted. Okay, now I'm starting to partition from the left side, smaller and smaller partitions. Now I'm partitioning the last quarter of the data, and I keep doing this, smaller and smaller. It's kind of fun to watch, right? Let's see what the next one is. All right. This is merge sort. Okay. So you'll see I'm building up larger merged sections from smaller ones, right? Merging. Now I've got, okay, those two come together into one big thing. And now essentially what I'm doing is I'm working on the right side of my array, right? So anyway, this is pretty awesome stuff. I hope you guys enjoy it. Let's see here. I got to figure out how to get this slide to advance one more. That's all I have. Feel free to ask questions about sorting on the forum. So let's see here. There should be a new version of the slide. Yeah, so I'm still holding office hours online at the times that are indicated on the calendar. Typically nobody comes. It's a little sad. You guys are certainly welcome to drop by and say hi. I'll try to make sure I announce this on the forum as well. Anyway, I hope everybody is safe and doing well, taking good care of yourself and the people around you. Hope you guys did well in today's quiz. And get started on your final project. So this is a good time to find a partner, start to talk about some ideas of things you might work on. We do have a checkpoint for the final project due in lab a week from next week. Next week's lab's on sorting. All right, I will see you guys on Wednesday. Enjoy the rest of your day.